students. We are from Group 2A. We'll present about Project 1 is FEA analysis of bike frame in subject computer simulation BMKT 3453. My name is Muhammad Zainal bin Musa and with me is Muhammad Afiq bin Matnawi and Yap Hujian. Next is background. So a bicycle frame has to be strong enough to hold the rider and deal with different force, like when you are pedaling, braking, or going over bump. At the same time, it should be as light as possible, so it is easier to ride. In the past, checking if the frame was strong enough to took a lot of time and was done by hand. Now, engineers use computer software like ANSYS to test the frame using something called finite element analysis or FEA. This method lets them see how the frame will handle different force quickly and without needing to build a real bike first. Okay, next is objective. The main goal of this project is to test how strong and safe bicycle frame is when used in real life situations. To do this, we use computer software called ANSYS Workbench 2022 and a method called finite element analysis or FEA. First, we use static structure analysis to see how the frame react when steady force are applied, like when someone is riding the bike. Next, we did a stress and deformation evaluation to find out the highest amount of stress and how much the frame bends under different load. Finally, we did a safety and design validation. This step checks if the frame stays within same limit based on the strength of the steel material. This helps us make sure the frame is safe to use and design well. In this part, we look at the shape and size of the bicycle frame, which is called the geometry. Okay, on the left, we have the general geometry. This is a standard frame designed from published source. It shows all the important parts of the frame, like the top tube, seat tube, and chain stays, all with label dimension. This is based on traditional or typical bicycle designs. So on the right, we have the project geometry. This is our own custom frame model created using CAD software. We made some design change but still follow the same measurement as the general geometry. So both are synchronized. This helps us compare design with our modified one and test how well it performs.
Assalamualaikum warahmatullahi wabarakatuh. My name is Maafi Malawi. My meter number is B13231068. Today I can explain about general discussion. We will continue about purpose of general study to compare structure and different loading on bicycle frame. And then my title general discussion I get in Scopus. My title journal is Stress Analysis of Bicycle Frame. You can see is normal stress, maximum stress in journal. Okay, and then we will continue about methodology. The standard bicycle frame geometry I'm creating SolidWorks, and then this frame include as like top tube, down tube, rear wheel, front wheel, and then change this. We use material is carbon fiber. Okay. After that methodology, we continue about boundary condition, fixed condition. We apply fixed support, I put front and rear, and then a wheel hub. You can see first geometry. I put we support at front, and then you can see second geometry. I put the rear wheel hubs. Okay, now I can explain about force. You can see is two geometry. First geometry is apply load is 700 Newton. Well sit on the bicycle is bicycle not moving. Just panel begins, and then we assume system to be vertical equilibrium, and then factor 2G to apply. Simulate sudden impact. A total increase to on frame is 1400 Newton. Okay, now I can explain for validation error. We are compare equivalent Van-Mison's stress result with journal data to check accuracy. Error was calculated using this formula. Journal minus our result over journal multiply 100. We did mesh convergency study to check FEA accuracy. Simulation use three methods: cost, medium, and fine. Maximum stress result for each mesh we compare. You can see this table. I calculate medium and fine. Medium I get 1.72%, and then fine I get 13.31%.
Hi, my name is Yap Hong Jian. My metric number is P132310620. So now I am presenting the FEA under three different routing conditions. So the FEA was performed on the bicycle frame under three different load cases. For the each cases use different force, magnitude, and location to simulate real riding condition. The goal was to identify stress concentration area. So from the figure 1, you can see this is the first loading condition. It was simulate front impact from an obstacle. We applying 500 Newton force at the head tube, and the stress is concentrated at the head tube and down tube junction. So the result is highest von Mises stress observed in the low front triangle. This indicates potential weakness in frontal collision or pothole impact. The maximum stress recorded is 0.04906 MPa. Now is second loading condition at the below figure. So this is we simulate for rear impact. We are applying 1000 Newton at the seat stay. This simulates landing from a jump or heavy rear load. The stress is concentrated near the seat stay bottom bracket junction. So this area is critical for frame strength and durability. The frame show moderate stress level, so which means performance is acceptable. The result is the maximum stress recorded was 17.743 megapascal. Now is the third loading condition. This loading condition is simulated as a strong frontal impact. Example, hitting a crab or sudden stop. So we are applying 900 Newton at down tube. The results show the maximum stress was 7.4287 megapascal. The red zone near the down tube indicate high risk of yielding. The blue zone near the top tube and rear stay show low stress. The stress distribution show localizer impact with minimal speed. So now we are doing the comparison between these three loading conditions. We are summarize and compare with maximum deformation and maximum von Mises stress. We are highlight most affected area under each load. So from the result, we can see that the heat tube impact has the lower maximum stress value, which is 0.04906, but it has the highest maximum total deformation value, which is 1.4257. So for the second loading condition, seat stray impact, it has the highest value for maximum stress, which is 17.743 megapascal, but it has the lower maximum total deformation value, which is 0.5032. So for doing the safety of factor, we will choose the highest value of maximum stress. From the result, we were choosing 17.743 megapascal value, which is the seat strike impact loading condition. Now, we need to calculate safety of factor. Factor of safety is the ratio of yield strength to maximum stress. It ensures the design is safe under load. A higher safety of factor means a safer, more conservative design. From our project, we need to get the value of safety of factor below 3.0. To get the value below 3.0, we use the formula maximum von Mises stress equal yield strength of material divided by safety of factor. So, to find our maximum von Mises stress, we use 230 divided by 3. Then we will get 76.67 megapascal. After we get this value, we will input in SSYS and run the simulation. After we run the simulation, we know that a 4,320 Newton force have to apply at the seat straight to produce a maximum von Mises stress of 76.67 megapascal. This loop will give a factor of safety just below in 3.0 in SSYS. So that's all from us. Thank you.